Welcome back, everyone, and today we're finally going to begin nomenclature and learning how to name organic compounds. Particularly, I'd like to start with alkanes, which are just carbon and hydrogen single bonds. So over here, this is an alkane. It's all carbon and hydrogen bonds that are all single bonds, and we're going to learn some rules for naming them. And the first rule that I'd like to start off with is identifying the longest chain, which we call our parent chain. Now, in this case, that's what we're going to do here. We're just going to learn how to determine the longest parent chain. And also, I want you guys to know that if there's a tie for the longest chain, so if there's two chains that give you the same amount of carbons, the longest carbon chain, then you have to pick the one that gives you the most substituents. And substituents are just kind of the branches that are branched off of the main chain. So let's start off with this example. Over here, if I want to find the longest parent chain, I guess I'll start over here. So I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I got something over here. So I guess I'll just circle that in red so far. And that's 10 carbons, usually a good hint that it's going to be the longest one. But let's just check if there's anything else that has more or the same amount. So once again, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, if I look over here now, I do have another 10 carbon chain, and now I have to compare both of them. Well, if I look at the one that I've kind of circled in red, so this right here, I look at how many substituents, so how many things are branched off. 1, 2, 3, 4. I have 4 substituents. And if I look at the other carbon chain that I made with the one that's going this way, it only gives me 2 substituents, this one and this one. So I know that the one I circled in red will be my longest chain, and since it's 10 carbons, it'll be decane. So I assume that you already have your prefixes down. So now that we've kind of learned how to identify the longest parent chain, let's look at substituents and how we exactly, first of all, name the substituents. So, for example, when you're naming a substituent, let's say it's a substituent with 2 carbons, instead of being called ethane, we drop that A and E ending and add a YL, so it would be an ethyl group. So same thing if we had just 1 carbon, then it would not be methane, but drop the A and E ending and put a YL, so methyl. So methyl, ethyl, propyl, etc., etc. So you just drop the A and E ending and put a YL. So I guess we can do another example. Actually, let's just stick to this example. If I look at this longest carbon chain over here, I notice it has 4 substituents. Well, this substituent just has 1 carbon right here, so I know this is going to be a methyl group. And then there's another 1 carbon substituent, so this will be a methyl group. If I look over here, this is a 1, 2, 3, 4 carbon substituent, so it'll be a butyl. And since this is 2 carbons, it'll be an ethyl. So that's kind of how we just name substituents. So now what I'd like to focus my attention on is ring structures. And generally when an alkyl group is attached to or connected to a ring, the ring structure is generally considered the parent chain. So let's say, for example, we have an example like this. So we have this ring structure. So this is a 6 carbon ring structure. And let's say we have something like this. So I know this is 1, 2, 3, 4, 5, 6 carbons. And I know this branched alkyl group is just only 3 carbons, right? And now what I do is, since this ring structure has more carbons than the alkyl group, this ring structure will be my parent chain. And typically, if this was just a normal alkane, we would call it hexane. But when there's a ring structure that's the parent chain, we put a cyclo in front. So since this is indeed 6 carbons, it isn't hexane, but since it's a ring structure, we put the prefix cyclo in the front. So it'd be a cyclohexane. And same thing if this was 4 carbons and this was 3 carbons, this would now be a cyclobutane. And this, of course, since it's just 3 carbons, is our substituent, and it's a propyl group. But now what I want to focus our attention on is not always is this ring structure going to be our parent chain. So for example, if I gave you an example like this, what I notice is that this ring structure has 3 carbons, but my alkyl group has 1, 2, 3, 4 carbons. And I know that the 4 carbon chain is longer than the 3 carbon chain, so this has to be my parent. And this ring structure has to be my substituent because it's less carbons. So in this case, we know that this will obviously just be a butane. What about this? Well, normally if it was just a normal substituent, it would be called propyl. But when it's in a ring structure and it's a substituent, we do the same thing. We put the prefix cyclo in front, and then we put the word propyl. So cyclopropyl. And let's say if this was 5 carbons long and this was only 4 carbons long, then yes, our parent chain would be pentane, and this would be cyclobutyl. So I hope that kind of makes sense for ring structures. So now what I'd like to focus my attention on are, well, actually before I do that, I'm going to just kind of lay this one out right here. What if I gave you something like this? So indeed, in this case, this will be my parent chain, but look at the substituent. It's branched. It's not normal like the other ones. So if I look over here, I got 1, 2, and I can either choose to make this my third carbon or this my third carbon. I guess I'll make this one my third carbon. And we have another methyl group coming out at the second. So this is kind of a branched substituents. So what I like to call these are complex substituents because they're branched. And how would we go about naming these? Well, exactly how you would name this is exactly how I've kind of laid out these numbers right here. Find the longest chain in the branched substituent, and then look at where the secondary substituent is coming out. So we know that it's coming out at the 2 carbon. There's a methyl. So how I would name this would now be a 2-methyl, and then since it's 3 carbons long, it's not going to be propane, but it's going to be propyl. And the reason why it's not going to be propane is because this isn't our parent chain. It's just a branch substituent. This over here is our parent chain. So it would be a 2-methyl propyl. And there's these common complex substituents that I have right over here that you're most likely going to be introduced to throughout organic chemistry, and these are used quite a lot. So a good way is to just be able to list them using the traditional naming method. So for example, this right here would be a 1-methyl ethyl. So since there's a 2 carbon chain from here, 1, 2, and then there's a methyl group coming off at 1, that's where you get the 1-methyl ethyl from. But there's also these kind of common names: isopropyl, sec-butyl, isobutyl, tert-butyl, and isopentyl or isoamyl, and then neopentyl. So what I recommend is that you know how to name it both ways, because often what teachers will do is if they ask you to draw, instead of giving you already drawn a alkane and asking you to name it, what if they ask you to draw the structure out and they give you a word like isopropyl? You're going to have to know what it means. So that's why I recommend that you guys understand and know these common ones. So once again, you can pause the video, write them down, or look at them, and I'll let you do that. So yeah, I guess I'll move on now. So now that we've kind of got an idea of these complex substituents, what I'd like to start now is kind of getting the name assembling patterns out. So the number of carbons on the parent chain, we always number the carbons on our parent chain because those help us identify the location of the substituents. What do I exactly mean by that? Well, for example, let's say I draw something like this. First thing first is I have to name my parent chain. So 1, 2, 3, 1, 2, 3, 4, 5. That's my longest parent chain. And what I notice is there's a methyl group coming out here. So on the second carbon. So that's how I know it's going to be a 2-methyl, and then the parent chain pentane. So that's why we kind of like numbering our parent chains. But we always want to assign the locants to the smallest numbers possible. So for example, if I look at this, let's say look at this exact same example. But I start naming, numbering my carbon chain from here, 1, 2, 3, 4, 5. What I notice if I start naming it this way, the parent chain is the exact same as if I'm going this way. But notice now that I have that methyl group on the 4th. So this would be a 4-methyl pentane. And the reason why I wrote this down is to show you that this is incorrect. We always want to assign these, which we call the locants, the lowest number possible. So if we're going this way naming the parent chain, it gets a number 2, but if we're going this way, it gets a number 4. So therefore we know that we want the lowest number, so naming the parent chain this way is the correct way and not the other way around. So that's an important rule to remember. And when there's multiple substituents present, you always assign the number so that the first substituent gets the lowest number. But let's say, for example, you get an example where it doesn't matter which way you name the number of the parent chain, you get the first number as always being the same on each case. So for example, if I give you an example like this, let's say you had something like this. So if I label this way, I get 1, 2, 3, 4, 5, 6, 7. So I'd get a 2, 3, 4, so 2, 3, 4, 5. So I'd get a 2, 5, 5 if I'd label my parent chain going this way. But if I label it going in the other direction, so this starting as my number 1 position, 1, 2, 3, 4, 5, 6, 7, I notice that this is a 3 and a 3 and a 6. And I know that the first number 2 is smaller than 3, so therefore naming it this way is correct. And exactly, if, let's say, for example, hypothetically speaking, these two numbers are both a 2, then we would move on to the next number, and then the next number until we get the lower one out of the 2. So what I mean by that case is, let's hypothetically say an example you do gives you the number 2, 3, 6, and if you do it the other way, it gives you a 2, 5, and a 6. So since these first two numbers are the exact same, ignore them and focus on the next number. So 3 is smaller than 5, therefore the 2, 3, 6 is correct over the 2, 5, 6. So that's how it works that way. And with cyclos, it's the exact same rules. The exact same rules apply. So now, putting all of this kind of naming rules together, we want to make sure that our substituents are placed in alphabetical order. So let's say, for example, in this case right over here, I notice that there's a methyl group on 2, 5, and 5. I know that that means there's a total of 3 methyl groups. And what I'm going to do is I'm going to put the prefix tri before the methyl to indicate that there is indeed 3 of them. And if there was 2, it'd be di, and if there was 4, it'd be tetra, and so on and so forth. But when we're putting the whole name together, we want to put everything in alphabetical order. And when we're doing that, we don't count these di, tri, tetra prefixes. They don't count for alphabetization. What I will count for alphabetization is starting with this M. So for example, if I gave you a trimethyl and an ethyl, the ethyl will come first when you're going to put the whole name together before this methyl. And the reason for that is because this tri prefix doesn't count. Let's even say it was a dimethyl compared to an ethyl. The ethyl still gets placed first because in alphabetical order, E comes before M. We don't care about the di, tri, tetra prefixes for alphabetization. And another rule that I want to kind of point out is for complex substituents. Notice how there were some complex substituents that had isobutyl, isopentyl, and then there was a second tert butyl. So for complex substituents, the second the tert is ignored, just kind of like how this di and tri prefix is ignored for alphabetization, but iso is not ignored. So for example, if you were going to alphabetize sec-butyl and isobutyl, your sec-butyl would come first because you're not counting the sec or the tert in alphabetization, but you're counting that butyl, so B. And for isobutyl, you look at that I. So as it, once again, second tert do not count for alphabetization order, but iso does. I don't know why they made this rule, but that's how they made it, so we're just going to have to kind of abide by it. So now what I'd like to do is, since we kind of have all these kind of rules for naming down, what I'd like to do is kind of get some examples done, because more practice always makes better. So let's start off with this first example over here. First thing first, I want to identify my longest parent chain with the most substituents if there is a tie. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. There you go. That's my longest chain, and I know there can't be any other chain longer than it. So that is my parent chain. And now I want to consider, should I start labeling this being carbon number 1 and going 1, 2, 3, or going this way? Well, if I start labeling this way, 1, 2, 3, I get a methyl group on 2, a methyl group on 3, and then an ethyl group on 4. But if I start numbering my parent chain going this way, I get 1, 2, 3, 4, 5. I get my first substituent on 5, and then 1 on 6 and 7. So I know that's not right because I want the lowest locant numbers possible. So I'm going to start going this way. So this will be carbon 1, 2, 3, 4, 5, 6, 7, 8. So I have a methyl group on 2, 3, and an ethyl group on 4. I know that E comes before M in alphabetization, so that ethyl group is going to come first. So I have a 4, and then I put the dash, ethyl, to indicate that the number 4, there's an ethyl branch. And then I put another dash, and there's 2 methyl groups, 1 on 2 and 1 on 3. And I put another dash, and since there's 2 methyl groups, I put that prefix of di first, so dimethyl. And then since my parent chain is 8, so octane. Now this should all be written in one straight line. I just don't have enough room, so that's why I decided to put the octane down there. And notice how I don't really put any spaces. So therefore this octane should be over here, but I just don't have enough room. So be aware of that. In the next example, here I have a ring structure, and then I have a complex substituent. How I know that is because it's branched off. So in this case, this is 1, 2, 3 carbons long, and this is 6. So this will be my parent chain. So I know that this 6 carbon ring will be my parent chain. So cyclohexane will be my parent name at the very end. And now if we look at this branch substituent, if you go back to the previous complex substituents that I have, this is actually a sec-butyl. So since that's the only branch, that's the one I can put, it's a sec-butyl cyclohexane. And if I didn't want to use this sec-butyl and I wanted to do a traditional naming technique for the complex substituent, what it would be is, if I label this right here, it'd be a 1-methyl propyl cyclohexane. Both are correct. I personally prefer that one over there. But it's also good to know this, just in case you get a branched or complex substituent that's not in one of the common ones that I've mentioned, then this is the best way of going about it. So if we move on to our next example, identify my longest parent chain. So 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So in this case, if I go this way, I get 1, 2, 3 substituents. And if I go this way, I also get 1, 2, 3, 4, 5 substituents. So I get 3 substituents again, 1, 2, 3. So it doesn't matter which one I pick as my parent chain because both of them give me the exact same number of substituents. I'm just going to go this way, but if you go this way, you'll get the exact same answer, and you can even try it out yourself afterwards. So if I go this way, I have a methyl group on 2, an isopropyl group on 3, and then another methyl group on 4. So I know that I comes before M, so my isopropyl group on 3 will come first because it's in alphabetical order, so a 3-isopropyl, and then I have a methyl group on 2 and then one on 4, so since I have 2 methyl groups, a dimethyl, and now I've run out of room, so I'm going to put the parent chain, the pentane, right over here, even though it should be in one straight continuous line going this way. And now if we go over here, what I notice over here is that this ring structure is not my parent chain. My parent chain actually is 1, 2, 3, 4, 5, 6, 7, 8 carbons long. So going this way. And that this is just a substituent. So if this is a substituent, it's going to be a cyclohexyl. And then that's alphabetized with a C. So C comes before the ethyl or the methyls. So therefore it'll be first. And since it's on the second carbon, a 2-cyclohexyl. And then I have an ethyl group on number 4, remember alphabetical order, and then I have a methyl group on carbon 5 and 6, so a dimethyl octane. And that should also be in one straight continuous line, but I don't have enough room, so yes, that's what that one should be. So hopefully these examples have made sense. If not, no, pause the video, try to relook at them, and if it still doesn't make sense, you can comment down below or send me an email. So if we look at this next one right over here, I want to identify my longest parent chain. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's see if there's another one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I have 2. So if I go with my first one, I have 1, 2, 3 substituents. But if I go with my second one, I have 1, 2, 3, 4 substituents. So going this way, up here, ending over here is better because it gives me more substituents. And if I want to name it, so if I start numbering my parent chain carbons from here, I get 1, 2, 3, 4, 5. I get my first one on 5. But if I start naming from here, I get my first one on a 2. So it's better if I name from 1 to, well, number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 because it gives me the lowest locate numbers possible. So if I look over here, the ethyl in alphabetical order is on the 3rd carbon. And then there's an isopropyl on 1, 2, 3, 4, 5, 6. And then there's on the 2nd and the 4th, there's a dimethyl. And then our parent chain is decane. Or you could have written it by, so instead of writing 6-isopropyl, what you could have done is you could have done, I'll just write it up right over here, I guess. Instead of writing 6-isopropyl, what you could have written was 6- and then an open bracket 1-methyl ethyl. And then you could have continued on from there if you wanted. So, yes. So 3-ethyl-6-isopropyl-2, 4-dimethyl decane. Or if you wanted to replace isopropyl with, let's say, for example, the other traditional naming scheme, then it would be a 6- open bracket 1-methyl ethyl close bracket. So if I did this last example now, I want to find my longest parent chain. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So I have 2. And remember, if I go 1, 2, 3, 4, 5, 6, 7, I get 2 substituents. But if I go 1, 2, 3, 4, 5, 6, 7, I get 3 substituents. And if I wanted to name this, so I have 1, 2, 3. This gives me the smallest number. This would be a 1, 2. My first substituent number would be a 2, but if I started from here, it'd be a 1, 2, 3. So it's better if I go 1, 2, 3, 4, 5, 6, 7. And if I name this, it would be, there's an ethyl group on number 3, and then there's 2 methyl groups, one on 5 and one on 2. Dimethyl, because you have 2 methyl groups, and then the parent chain of heptane. So yeah, that's how you would do that one. And notice how I always, since I have 2 methyls, I always put the lower number first, followed by the larger number. So now, what if we were asked to reverse the order? Sometimes instead of having to just name the structure given to you, what if you're expected to draw it with the name given to you? And how I like to approach these problems is I like to start off with my parent chain. So I notice this is a pentane. So it's going to be a 1, 2, 3, 4, 5 carbons long. 1, 2, 3, 4. 1, 2, 3, 4, 5. So actually, I did that one correctly, so let's do it over here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yes. And now I know that there's a methyl group on 2, so I'm going to say, now you pick which side you want to start from. Let's start from this side. So I have a methyl group on 2, a methyl group on 3, and then a methyl group on 4. So that's how you would do that one. Actually, no. I'm sorry, this is incorrect as well again. 1, 2, 3, 4, 5. There's 2 methyl groups on 2, so 1, 2, and then a methyl group on 4. So yeah, if you wanted to go this way, if you wanted to start numbering them this way, it doesn't really matter. Then you'd have another branch here, and then this would just be a single branch. So let's draw the next one. Now 1, 2, 3, 4 dash tetramethyl cycloheptane. So first of all, I always like to start with my parent chain as cycloheptane, and don't really like drawing these because they're quite difficult to draw. 1, 2, 3, 4, 5, 6, 2, 3, 4, 5, 6, 7. 2, so 1, 2, 3, 4, 5, 6. I really hate drawing these ones. I'm not really good at drawing the cycloheptane, so let's try this one again. 1, 2, 3, 4, 5, 6. So 5, 6, 7. Oh, that one's not right again. Yeah, 1, 2. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Oh my god. Let's try this one again. I'm sorry guys, this is really hard to draw. 1, 2, 3, 4, 5, 6, 7. Okay, let's try this one last time. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. That's the best I could do. So there's going to be a methyl group on 1, so I'll let this be 1, I'll let this be 2, I'll let this be 3, and let this be 4. So definitely in these you get more of a kind of choice on how you want to go about drawing your structure. And now the last one, so I'd like to start with the last thing, a pentane. So 1, 2, 3, 4, 5, and then there's an isopropyl group on 3, so I guess I'll let this be my first carbon, my second, my third. So if there's an isopropyl group right there, so this is kind of a case where you should be able to recognize what an isopropyl group is. And then there's a methyl on 2 and 4, so that's how you would draw that one. So those are the kind of examples I wanted to go through. Hopefully this makes a lot more sense to you, and definitely this is something that you should be practicing and get really good at because it's a very important skill to have. So once again, if you have any questions, comments, concerns, you can email me down below, and yeah, thanks for watching.